Welcome everyone to the wonderful world of 11.8. We're finally getting in to power series, aka infinite polynomials. And we kind of started this journey of chapter 11 saying that right when Newton wanted to integrate a function, he would quite often turn it into an infinite polynomial, and then just integrate it that way. So all of this stuff in chapter 7, these were like really Leibniz and Leibniz group followers and whatnot. But we're finally getting to the point where we're turning things into infinite polynomials. Well, almost anyway. So in today's class, right, so let me go ahead and pull up our video notes. Again, these are the things that you should have watched before you're watching this video right here. So this is all the stuff for 11.8. We bring up these things power series, aka infinite polynomials. So you can see that these polynomials, they go on forever. And again, we're very interested if they converge or diverge. This would be a power series centered about 0. That would be another way to say this. And in general, if you have a power series centered about a, then you have a lot of these x minus a's in it. Notice that you could always, of course, write x minus 0. So that would be the same thing as x. Okay, so these are what power series are. They're really just a fancy term for infinite polynomials. And the primary goal for this section is to figure out when do these infinite polynomials make sense and when don't they make sense. AKA, when do they actually go to a real number versus when do they just go to infinity or negative infinity or they just don't make any sense whatsoever. AKA, when does the series converge and when does the series diverge, right? So that's what I mean by making sense. So we got this beautiful theorem right here. This is kind of the one that we need to really look at and understand. It says that, for a given power series, really there's only 3 situations that can happen. Maybe it converges only at a specific point, only at the center, only when x is equal to a. And in which case we would say that the radius of convergence would be 0, right? That you can't take any step off of your center. Once you take the tiniest step off the center, this power series no longer makes sense. Well, that's not a very interesting power series then, right? The other thing that can happen is that maybe the power series converges for all x. That is, it makes sense no matter what x you plug in, it makes sense. It goes to some real finite value, and that's very satisfying. And in that case, you would say that the radius of convergence is infinity. And then what happens most of the time, at least in this class anyway, is that maybe it converges some of the time and maybe it diverges, some of the other time, some other time. And so in that case, there's some positive radius of convergence. And again, it's centered about a. And you can take that radius of convergence, you can take that many steps off of a and it'll converge. However, if you go more than that, it will diverge, in which case you're said to have maybe an interval of convergence, right? So you could go ahead and specify what the interval of convergence is, and that's exactly the game that we're playing in today's class. We'll see we're going to do 4 problems in great detail, and in each one of them, we're very interested in, does the power series converge, right? When does it converge? When does it diverge, right? Find me that interval of convergence. That's really the game that we're playing in today's class. So in all of these, let me go ahead and maybe flip over to my class notes for today. Oh, oops. Next one down. There we go. So in this class notes, I've just said, I've nicknamed these given a power series. So in every single one of these, we will be given a power series and we want to know when does it make sense, when does it not make sense, aka when does it converge and when does it diverge. Later on, we'll be generating these infinite polynomials. That is, if we're given a function or maybe we have some function and we want to turn it into an infinite polynomial, that's a game that we'll eventually play. But for right now, we just want to know when does it make sense, when does it not make sense. So, all right, here we are. Example 7, find the radius and interval of convergence for this power series here. That is, we have kind of our standard series, things with n's in it, and then we have the x's, right, the variables here. And we want to know what x values have this converge and which x values have this diverge. And so the big thing in every single problem throughout all of 11.8, you probably saw that there was this trend, and we'll see it again here for our 4 examples in this here video, that every single one of these 11.8 problems, we're going to use the ratio test. The ratio test, the ratio test, over and over and over again. It's our favorite test, and this is what we need in order to show that, what the interval of convergence is. And so yes, we are going to start off every one of these ratio test. And so what the ratio test says is that, again, the limit as n goes to infinity, and we need our a sub n plus 1. So everywhere I see an n, I'm going to plug in n plus 1. So we have -3 raised to the n plus 1. We have n plus 1 on bottom. We have root n plus 1. And I guess technically that x is also in the numerator. Let's go ahead and put it in the numerator there. N plus 1, x to the n plus 1 there. And then we need to divide by a sub n. Well, I'm just going to multiply by the reciprocal here. So I'm going to have n, root n, and then in the bottom we have -3 to the n and x to the n. All right, so we need to go ahead and evaluate out this limit, and it will converge, aka this power series will make sense if it's less than 1. So let's go ahead, spend a little bit of time trying to evaluate out this limit. Now, very similar to 11.6, what we did is that we gathered up all of the like terms. So I'm going to go ahead and I'm going to group up all these -3's raised to powers. I'm going to group all these x's raised to powers. I'm going to group together all of these linear things, right? N on top and n plus 1 on bottom. And I'm going to group together all of these square roots. So square root on top, square root on bottom, all with these absolute values here. And now some of these, there's actually quite a bit of canceling that happens, right? So for instance, with those -3's, right? We have one more -3 on top than we do on bottom. And so pretty much they all cancel except for we're left with one more on top than we have on bottom. And so we could go ahead and rewrite this. The limit n goes to infinity. The absolute value of, and again, we have one more -3 on top than we do on bottom. And likewise, for the x's, we have one more x on top than we have on bottom, right? N plus 1 x's on top, n x's on bottom. They nearly all cancel, but we're left with just regular old x on top. All right, here we don't quite get any canceling to occur, but let's go ahead and just leave these as is. Actually, with the square root, we could go ahead and put this all inside of one big old square root here, something like this. And this is still within our absolute values. Let's go ahead and try to take care of those absolute values here. So now let's go ahead and apply these to each one of these pieces. Remember, you're allowed to essentially distribute the absolute values across multiplication. So this is just going to be 3. Now the absolute value of x, this is the only one, right? We don't know what x is right now, right? X is a variable. X could be negative. It could be positive. I'd love to just be able to get rid of the absolute values, but sadly I can't say for certain that they don't matter, right? If x was a negative number, it would really matter. If x is positive, fine, it doesn't matter, right? But if x is negative, we need to keep these here just in case. Now n is something that's going off to infinity, right? So again, think of it as something very large, a million, a billion, a trillion. That's certainly all positive stuff. So I don't have any problem here saying that these are going to be positive values. And again, square roots only output positive values. So I'm quite certain that the absolute value does not need to be applied. Or when we apply it, it's just the same thing as what we input into it. All right, now, as the limit, as n goes to infinity, of course, 3 stays the same. Absolute value of x stays the same. Now, this is a polynomial on top, polynomial on bottom. They're both degree 1, and so it's going to be this ratio of their leading coefficients, 1 over 1. That's just going to be 1. And then same sort of deal here, but now the answer is inside of a square root. Essentially here, we're pushing the limit inside of the square root. And again, we have the leading coefficient on top and bottom are both 1. So this is going to be the square root of 1. And again, what we're searching for, what we're hoping for, in order for the ratio test to make sense, in order for this to converge, we would love for this limit to be less than 1. And so we can go ahead and maybe simplify this down here, right? 3 absolute values of x's should be less than 1. That's to say that the absolute value of x should be less than 1/3. And notice, right, once we have it in this form right here, we're actually very close to saying what the radius of convergence is. So notice for the radius of convergence, that's one of our tasks that we need to answer here. Let's go back. Oops, I forget that they always reorder themselves based on what the last one I clicked was. But let's go ahead and look at this third scenario here, right? If there's a positive number r such that the series converges if x minus a, that absolute value, is less than r, right? So notice that we could go ahead and rewrite our situation here as, for instance, x minus 0. And this makes a lot of sense, right? Because our center is at 0, right? You don't see any like x minus 1s or x minus 5s or anything like this, right? This is a power series centered about 0. And so we can see if we go ahead and rewrite it in this fashion, that 1/3 right there, that is the r value. Our radius of convergence quite literally is 1/3 because we were able to write it in this form. All right, next up, the interval of convergence. So the interval of convergence, this really helps us, there's an old algebra theorem that actually comes in very useful here, which says, how can we rewrite absolute value inequalities? And it says that the absolute value of some expression being less than a positive value k, that this occurs if and only if a is greater than negative k and it's less than k. So this is very nice. Let's go ahead and use that down here for ours. So our expression is the absolute value of x. So we could go ahead and rewrite this as x being less than 1/3, and greater than negative 1/3. So in this case, right, my k value is 1/3, and my a value, right, what's inside of the absolute values is x minus 0, or just x. And so using this nice algebra theorem, we can go ahead and rewrite this, and we can see that anywhere between negative 1/3 and positive 1/3, this series will converge. The problem is, right, so we're like 99% even, of the way there. But the question is, right, the ratio test is sometimes inconclusive, right? It doesn't know. And that's when the limit is equal to 1. This is equivalent to at these endpoints, right? So it doesn't know if this should be less than or equal to 1/3 or greater than or equal to negative 1/3. The ratio test isn't going to be able to detect when this, right, is really equal to 1, essentially is what this comes down to. And so what we always need to do is check our endpoints. And I guess I should be a little bit more specific here, right? If it just says an interval of convergence, then we always need to check our endpoints. However, you'll see in WebWork, for instance, that sometimes, and this is true for quizzes and exams as well if they want to save some time, they'll just say, what is the open interval of convergence? And so for open intervals, you don't need to worry about your endpoints. And so in which case we'd be completely done. It'd be from negative 1/3 to 1/3, and that would be the final answer. However, in this case, it didn't say open interval of convergence. It says, what's the interval of convergence? And in which case, we have to go ahead and test those endpoints. So I'm going to literally test, what happens at x equals negative 1/3. And I'm also going to test what's happening at x equals 1/3. So those are my two endpoints. Those are the two things that I need to go ahead and test. So, okay, well, why don't we go ahead and take care of x equals negative 1/3 first. So again, quite literally, I'm just plugging into my series right here. X is equal to negative 1/3. So let's go ahead and do that. We're summing up, and we have this negative 3 to the n, and divided by n root n, and then times, and instead of x, I'm going to put negative 1/3. And that's what we raise to the nth power. And technically, we're going from n equals 1 to infinity, so I can include this as well. Now, in this case, right, we can see that we have a lot of stuff that's actually being raised to the nth power. So let's maybe go ahead and group all of that sort of stuff together, right? With rules of exponents, I'm allowed to rewrite this and combine all of this stuff as being raised to the nth power. Remember, we did this trick quite a lot when we were doing the geometric series test, right? We often wanted to get just one thing raised to the nth power. So in this case, I would have -3 inside, and I'd also have -1/3. Well, of course, these can cancel out a bit, and we're just left with 1. 1 raised to the nth power. And of course, when you take 1 and you raise it to who cares what power, right, you always get 1. So in this case, we just get, summing up from n equals 1 to infinity of 1 over n root n, right? Because 1 raised to any power is just itself. Now in this case, we could actually simplify even farther, right? When you have root n, that's the same thing as n to the 1/2 power. And remember, when you're multiplying together two exponentials with common, or with a like base here, that those exponents add together, right? So I could go ahead and write this as n raised to the 1 plus 1/2, so that's going to be 1.5, or I could go ahead and write 3/2 power here. Now, for this, we can kind of quickly say that this is going to converge by the p-series. And so should it be included in our interval of convergence? Well, absolutely, right? This is a place where it converges. And so therefore, we should go ahead and include the point -1/3. And in order to include the point -1/3, of course, we change that parentheses to a bracket, right? Because that's what it means. That's the notation that we use to include the endpoint in interval notation. Okay, well, how about the other endpoint? So the other endpoint is at +1/3. So let's go ahead, and again, I'm just going to quite literally, everywhere I see an x, I'm going to plug in +1/3. So all this stuff is saying the same, and then I'm going to have +1/3 raised to the nth power here. Again, I'm going to do a similar strategy of trying to combine all of the stuff, right, that is raised to the nth power. So I'm going to leave this stuff alone here, and then combine. Here we have -3 divided by 3 to the nth power. Well, -3 divided by 3, that's just going to be -1. So this is actually an alternating series, right? We can see that this -1 raised to the nth power, this is going to be an alternating series. And in fact, if we kind of take a quick peek at just the positive piece, right, my mind is already going to the alternating series test, right? I'm interested in that positive piece. And I'm interested to see, right, is this decreasing? And does the limit go to 0? So in this case, yes, right? Because we just have a fixed numerator, 1, and the denominator is getting bigger, 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 going off to infinity, right? That this is decreasing, and the limit of just the positive piece goes to 0. So by the alternating series test, this converges as well. And so we would also want to include +1/3 in our interval of convergence. And so therefore, the overall interval of convergence is going to be from -1/3 to +1/3, and we include both endpoints, right? And by the way, right, if we were to, it's nice to kind of sketch these things as well, kind of in a number line, right? So -1/3 is down here. +1/3 is up here. And notice right in the center of between -1/3 and +1/3 is 0. I mean, quite literally, when we say that 0 is the center, right? Remember this 0 over here, that's the center, that it is in the center of this interval of convergence. And so quite literally, like if we were drawing this out back in our algebra days, right, first off, we'd start off by saying, right, it definitely converges everywhere between -1/3 and +1/3. And then using these tests here, right, first we checked at -1/3. We said, it converges there. It should be included in the interval of convergence. And we just quite literally plug in that dot, right? We fill that in and say that should be included. And also, x equals +1/3, right? So that also converges there. And so we should fill in that dot. So this is kind of the graphical representation of that answer from -1/3 to +1/3. Here you really see 0 in the middle. Again, our radius of convergence is 1/3. We saw that, and that quite literally is kind of, if you think about a one-dimensional circle almost, right? that this is, you can go 1/3 away from the center in this direction. You can go 1/3 away from the center in this direction, right? It's all connected here. So that's why we're using this terminology, a radius of convergence and an interval of convergence. All right. So that is the first of 4 problems. We'll go through the other ones a little bit faster, but it's nice. This is a good warm-up kind of what we need to be able to do in 11.8. All right, let's go ahead and move on to our second problem here. We're going to find the radius and interval of convergence of this thing here. Notice I'm making it a bit more challenging on us, right? I don't just have regular old x to the n anymore, but I actually have x plus 1 raised to the n. And so we need to see how does that influence things, right? So, okay, let's go ahead and we'll do this one together. I promise I'll give you guys a chance to work here on a few of the other ones, the ones coming up here. But let's keep it together here. And again, every single one of these problems, 11.8 problems, when you're given a power series, the way that you figure out this interval and radius of convergence is by applying the ratio test. So we're going to go ahead every single time. Ratio test is going to be the way that we start these. The limit as n goes to infinity of the absolute value of, and again, everywhere I see an n, I'm going to put an n plus 1. N plus 1 times 4 to the n plus 1. And then we're going to go ahead and divide by a sub n. That is, well, let's go ahead and multiply by the reciprocal. So I'm going to do n, 4n on top. And I'm going to do x plus 1 to the n on bottom. Again, all inside of these absolute values. Let's go ahead and start combining like terms. So x plus 1 raised to the nth plus first power divided by x plus 1 raised to the nth power. We have an n and an n plus 1. Those should go together. And we have a 4 to the n and we have a 4 to the n plus 1. Those should go together. Again, all inside of some absolute values. We see that there's quite a lot of cancellation here. We see that nx plus 1s cancel on top and on bottom. There just happens to be one more on top. And likewise, n4s cancel on top and on bottom. There just happens to be one more on bottom. So we have the limit as n goes to infinity, and we're going to have an extra 4 on bottom. This doesn't really cancel exactly here, and we have an x plus 1 left on top. Now let's go ahead and distribute these square roots, right? So the square root of x plus 1, again, I don't know what x is. Maybe it's positive, maybe it's negative. So I'm a little reluctant to say we can just get rid of those absolute values. In fact, it would kind of ruin things, right? We need those absolute values. If you remember in the video, right, kind of this really relies on us having these absolute values. And so we really actually want these things. So let's go ahead and leave them in, especially for the x's. I did it again. There we go. Now, for the n's, on the other hand, remember n's going off to infinity. This is certainly a bunch of positives, and 4 is certainly positive, right? So we can apply the absolute values to all those things. We don't have to worry about if they're accidentally negative like we do with the x's. And so as n goes off to infinity, well, x's don't care about n's. Here we have n divided by n plus 1. That's going to be 1 as n goes off to infinity. Remember just this ratio of the leading coefficients here. And we have 1/4. And again, with the ratio test, this will converge. Remember, we're very interested in finding what interval and what radius does this converge. And if you want the ratio test to say, hey, this thing converges, we want it less than 1. Okay, so this is the setup. Let's go ahead and do a bit of rearranging here. I'm going to bring the 4 onto the other side, right? Multiplying by 4 on both sides. And I'm going to leave the x plus 1 here. If we wanted to, we could rewrite this, and it could be even more suggestive. Remember, we're trying to make this look like x minus a is less than sum r. So if I wanted to, I could rewrite this as, instead of x plus 1, we could do x minus negative 1. So now we really see that our center is negative 1, and our radius of convergence is 4. So we now know at this point that our radius of convergence is 4. So we have figured out half of our answer. The other half of our answer is the interval of convergence. So in order to figure out the interval of convergence, again, I'm going to use this nice algebra theorem to go ahead and rewrite this and I'm going to rewrite it as negative 4 is less than x plus 1, and that's less than positive 4. So again, we're using this whole, right, a, this should be the k value, this should be the negative k value. So again, a is what's ever inside of our absolute values, and 4 should be that positive constant there. So, okay. There we go. Now we can go ahead and rearrange this. Subtracting by 1 across the board, well, 4 minus 1 is going to be 3. Negative 4 minus 1 is going to be negative 5. And so let me go ahead and bring up our picture a little bit early here. Last time I just brought it up at the very end. So I'm going to bring up 3. So let's see, 1, 2, 3 is going to be over here, and negative 5. 1, 2, 3, 4, 5. So negative 5. And already we know for sure that it converges between these things. And by the way, if you were to try to figure out what is the center between 3 and negative 5, you would find that it's here at negative 1, that the center of this interval is at negative 1. So in fact, we saw, right, our center here is indeed negative 1. Okay, now as always, right, this one says we just need to know what the interval of convergence is. It doesn't specify an open interval of convergence, and so we need to check those endpoints. So I'm going to go ahead and check what happens at x is equal to negative 5, and what happens when x is equal to 3. So those are my two endpoints, and we need to check those out. All right, so let's go ahead and plug these in back to our original equation. So let's see, summing up from n equals 1 to infinity. And everywhere I see an x, I'm going to plug in a negative 5. So negative 5 plus 1 raised to the nth power, n times 4 to the n. And why don't we go ahead and just write down for when x is equal to 3. So 3 plus 1 raised to the nth power divided by n times 4 to the n. Okay, so looking at the x is equal to negative 5. Let's go ahead and work on this a little bit, do a little bit of algebra here, simplify things down. Well, I'm going to have negative 4 raised to the n divided by n times 4 to the n. Again, just as before, let's go ahead and group together all the things that are raised to the nth power. And so, okay, 1 over n, that's just going to hang out here. I'm going to have negative 4 divided by 4. This is all raised to the nth power. Well, negative 4 divided by 4, that's of course just going to be the same thing as 1, right? Well, negative 1. And so, okay, we have this thing in alternating series. We look at the positive piece. We see that the positive piece is decreasing, and the limit of the positive piece as n goes to infinity would indeed be 0. And so by the alternating series test, that this converges. And so, okay, we would want to include this in our interval of convergence. So if I was going up here, I would say, okay, let's go ahead and include this. Negative 5 should indeed be included. So I'm going to go ahead and fill in that dot. Well, what about that dot at 3, right? How about our other endpoint? Well, let's go ahead and check. So let's simplify things down a little bit. 3 plus 1 is going to be 4 to the n. Again, we could go ahead and combine all of the things that have raised to the nth power here. So we'd have 1 over n, and then we'd have 4 divided by 4 raised to the n. Or you would just get 1 to the n in this case. Or that's going to be the same thing as 1. Notice that this is actually equivalent. Maybe some of you saw that, hey, these things should just cancel, right? And that's the same thing as just noticing that these cancel. So, okay, 1 raised to any power, or just having these cancel, we're going to be left with 1 over n. Now, does this converge or diverge? Well, sadly, it diverges, right? It diverges by the p-series. In this case, the p is equal to 1. And remember, whenever p is 1 or less, that this is going to diverge. So 3 in this case, it does not converge at 3. And so 3 should not be included in our interval of convergence. So our overall interval of convergence is going to be everything from negative 5 up to 3, but not including 3. So this right here would be my final answer as far as the interval of convergence goes. So we have our radius, and we have our interval. And by the way, just FYI, right, if you were to be here at our center and move 4 steps to the left, you would be at -5. And if you were to move 4 steps to the right, you would be at 3. So again, the radius of convergence, the interval of convergence, all these things are very much linked to one another. All right, so that is problem number 2. So a few things that we added here, right, is first of all that we had it centered about -1 instead of 0. So that was one upgrade that we made here. And also you can see that there was a case where one of our endpoints was included, but the other wasn't. Okay, so that's it for example number 8. Let's go ahead and move on to example number 9. I feel like I've been doing a lot of talking though, right? And I haven't given you guys a chance to really work on something. And so for this one, I think you should go ahead and pause the video, try this one on your own, get as far as you possibly can. Again, go back to these previous examples, go through the same sort of steps that we've been doing here, get as far as you can, and then we'll bring it together and go over the results together. All right, let's go over this problem together. So yes, we see here that again, over and over, we're going to apply the ratio test. That's the first place that you start with this. So you apply the ratio test. So everywhere you see, right, maybe an n, you plug in an n plus 1. And so you can get something like this. So n plus 1, don't forget in the bottom here, oops, there we go, n plus 1 plus an extra 2, so that's going to be n plus 3 in the bottom. And then you're going to divide by a sub n, or you can just multiply by the reciprocal. Now let's go ahead and combine all of the like terms. So we can do the n plus 1 divided by n, we can do the x to the n plus 1 divided by x to the n, and we can do n plus 2 divided by n plus 3. So those are all of our like terms. We can see that, again, there's a bit of canceling that happens. There's n x's on top, n x's on bottom, and there just ends up being one more left over on top. So we can do something like this. Now we can go ahead and distribute that absolute value to each one of these pieces. And when you take the limit as n goes to infinity, this bit right here, well, the leading coefficients are 1 and 1, so you're going to get 1 divided by 1. And likewise here, the leading coefficients are 1 and 1. And they're polynomials of equal degree, so that's where this one comes from. Now the absolute value of x is just the absolute value of x, right? We can't really necessarily simplify this down at all. We don't know what the value of x actually is. And so we can write down that the absolute value of x should be less than 1 if we want this to actually converge. Or to be more explicit, right, we can see that the center is going to be 0 and the radius is going to be 1. So now we have one of our answers, right? What is the radius of convergence? Well, the radius of convergence is 1. So, lastly, in order to figure out the interval of convergence, well, first of all, we could figure out the open interval of convergence just by using that great algebra theorem, and we know that it's going to be between -1 and 1. However, we need to figure out what about at these endpoints. So at the endpoints, we can go ahead and plug in these specific endpoints, right? So here we have plugged in x equals 1. Here we've plugged in x equals -1. So again, this is the work for x equals 1, and this is the work for x equals -1. And so when you plug in x equals 1, for instance, you get this series here. And you can sit with it for a little bit and try to figure out, does this series converge or diverge? And you can go through those steps that we had back in 11.7. Ugh, brain fart, right? So you can go back through those steps from 11.7 of how do you figure out, given a series, does it converge or diverge? And you'll find by the nth term test for divergence, right, that when you take the limit as n goes to infinity, that indeed you get 1. Well, 1's not 0, and so therefore it diverges. Now, likewise, if you plugged in x equals -1, well, this same kind of n divided by n plus 2 sort of business here, this is going to be going to 1 in the long run, but now it alternates. It goes between -1, +1, -1, +1. And so in this case, it will also diverge by the nth term test. But in this case, right, this limit does not exist, right? It doesn't go to any one particular real value. It actually kind of oscillates between 1 and -1, 1, -1, so on and so forth. And so, but that's certainly not 0. And so, okay, it will also diverge. So because it diverges at 1, and because it diverges at -1, the overall interval of convergence happens to be -1 to 1, and you don't include either endpoint. So I was pretty particular about these examples that I've chosen here. I wanted to show you one where neither of the endpoints were included. I wanted to show you one where one of the endpoints were included. And I wanted to show you one where both of the endpoints are included. So any of these possibilities can certainly occur, right? So any of them are possible here. And so you really do have to check. There's not a way to just quickly kind of look at this and say, definitely, the endpoints certainly shouldn't be included. You have to check. All right, I have one more problem for us to go over. This is kind of the most difficult one yet. Again, I think it would be wonderful if you could pause the video. You should try this one on your own, and then we'll go over the results together. So please pause the video, give it a go. All right, so this is how far I made it. Maybe you made it farther, and that's great and everything, but this is where I really want to start talking a little bit about a few things. So the first off here is that when you go ahead and you plug in n+1, notice that this is what replaces n, and so this 2 needs to be applied to everything. So you should distribute this, and you should get 2n plus 2 in the following line. So again, I guess I even skipped over it, right? I just assumed we're using the ratio test. We always use the ratio test for these sorts of problems. So we're here using the ratio test. Then we start to combine like terms. That's what the second line has traditionally been. And then we can go ahead and start to cancel, right? So there's 2n on top, 2n of these x minus 5s on bottom. So notice what happens in this case is that you're actually left with 2 of these x minus 5s now on top, rather than just 1. So that's something that's different going on here that we didn't see in some of those previous examples. Now, for the 9s, on the other hand, this is a little bit more classic. There's 1 more on bottom than there is on top, and so this is just going to be 1/9. Now, as n goes to infinity, well, you search around and, well, there are no n's, right? So as n goes to infinity, all these things say, well, I don't really care about n. I have nothing to do with n. So I guess we could go ahead and distribute these absolute values, right? So I can make this the absolute value of x minus 5 squared, and the absolute value of 9 is just 9, or the absolute value of 1/9 is just 1/9. And again, for the ratio test, every single time, if you want the ratio test to come out and say it converges, then you're looking for this limit to be less than 1. So let's go ahead and rearrange at this point, bringing this 9 over to the other side. And now, again, we're trying to make this look like some x minus a is less than r. So the square is standing in our way. And so the question has to be asked, is it all right to just take the square root on both sides of an inequality like this, right? And then maybe that 9 becomes a 3. And the answer is yes, because the square root is an increasing function. It's going to adhere to these inequalities that we have set up. And so yes, this is perfectly fine. And so we can see that our center is 5 and our radius of convergence, our first answer here, the radius is 3. Of course, we knew that the center was 5, right? Just by looking at it up here, we have x minus 5s. And so we could have verified our center, just from the statement of the problem. But here, radius equals 3. That's some new information that we didn't know about. So let's go ahead and work towards an interval of convergence now. So for an interval of convergence, we need to go ahead and maybe rewrite this using that wonderful algebra theorem. So it's going to say a, so x minus 5 in this case, the thing that's inside of the absolute value, that needs to be less than k and greater than negative k. So we can go ahead and rearrange here, and adding 5 across the board, we can see that x should be less than 8 but greater than 2. And so if you'd like to, we can go ahead and draw a little number line as well. So maybe here's 5 in the center of the number line, and if we move 3 to the right, we're going to get 8. If we move 3 down, we're going to get 2. And so 5 is right in the center there, and there is our interval of convergence to date. But just as before, we have to look at those endpoints and figure out what is happening at those endpoints. So the endpoints, again, are x equals 2, and x equals 8. So let's go ahead and plug these in and see what's going on. Again, so we're summing up from n equals 0 to infinity, and we have x minus 5. So 2 minus 5 raised to the 2nth power divided by 9 to the n. And likewise, when we plug in x equals 8, we're going to be summing up from n equals 0 to infinity, the quantity 8 minus 5 raised to the 2nth power divided by 9 to the n. And so let's see what's happening here. Well, in this first case, when we take 2 minus 5, we're going to get negative 3. And when we raise negative 3 to the 2nth power, well, remember, we're allowed to go ahead and do this one at a time. So when you take negative 3 and you raise it to the 2nth power, that's the same thing as if you took negative 3 and you raise it to the second power, and then you took that and you raise it to the nth power, right? You can do these things kind of one at a time. So if I was to take negative 3 and raise it to the second power, negative 3 times negative 3 is going to be 9, and then that I still have to raise to the nth power. And so I have 9 to the nth power divided by 9 to the nth power. These are going to perfectly cancel out. And of course, we're just going to be summing up 1 over and over and over again. And when you sum up 1 from n equals 0 to infinity, right, if you add 1 to itself infinitely many times, will this converge? Absolutely not, right? It's going to go off to infinity in this case. A way to formalize this would be with the nth term test for divergence, it will diverge. So in either case, right, this is certainly going to diverge, and it should not be included in our interval of convergence. Now over here, this one turns out to be even a little bit easier. In fact, when you take 8 minus 5, you just get regular old 3, and you raise that to the 2nth power. Again, you're allowed to go ahead and do these one at a time if you'd like. So 3 raised to the second power, that's going to be 9. Then take that and raise it to the nth power. And so you get 9 to the n divided by 9 to the n. Again, these things perfectly cancel, and you find yourself just adding 1 to itself over and over and over again. And of course, this is going to diverge, again, by the nth term test for divergence. And so in this case, again, we're not going to include in 2. It doesn't converge there. We're not going to include 8. It doesn't converge there either. And so the final answer for our interval of convergence is going to be from 2 to 8, and we include neither of the endpoints. All right, that is it for me for 11.8. I hope you guys enjoyed. Again, you're going to use the ratio test kind of over and over and over again. And our goal for this, we really only have kind of one flavor of question that's really a classic, and that is, what is the radius and what is the interval of convergence? Next time in 11.9, we're going to be interested in creating our own power series. So if we have a function, right, how do we turn this into an infinite polynomial? How do we make it a power series? So we are going to be asking some more interesting questions coming up, but right now we just want to know, when do these things make sense and when don't they make sense? I hope you guys enjoyed. I'll see you next time.